Welcome to Explorer's Guide Maritime Academy. This is Captain Gary. What I want to do is review coastal navigation. And what I mean by a review is I assume that you've gone through the presentations that we have online and you have done the work exercises. That's very important so that you have a base knowledge. This is simply a review to bring home all the finer points. In the past, I've had people flunk plotting, and upon talking to them, they pretty much assumed that they knew everything that they needed to and didn't bother to go through the presentations. As we're talking about a very basic core part of navigation, it's important that you understand those basics. Yes, we have GPS. Yes, we have a lot of other things going for us, but it's very important to understand the basics because that's what we have to rely upon, especially in emergency situations. So again, let me go through them. Let's do a review. One of the big changes, of course, is that the FAA no longer will sell charts, lower charts, to any retailers. There are a few people out there who will print on demand, but due to budget cuts, charts per se are no longer available except for these other companies. That's one of our bigger changes that has happened. Okay, on any time we deal with charts, we deal with both coastal charts that are set up on one set of scales, basic nautical miles, and then we have our inland charts, Great Lake charts, that are set up on statute miles. One of the big mistakes people make when dealing with Great Lake charts is that they forget how to use the scale down here, which is statute miles. If it's in miles per hour, then you have to have statute miles. If it's in knots, then you have to have nautical miles, and vice versa. If you have information that's based on knots, you must use nautical miles. If it's based on miles per hour, you must use statute miles. And again, it's a scale here that we would use. Most of our charts are Mercator charts. It's Mercator projection. Talked about that. In a Mercator projection, 1 degree equals 60 nautical miles. 1 minute equals 1 nautical mile. And to do measurements, distances, we use the longitude scale. The minutes that are broken down into tenths of minutes. We don't use seconds on plotting unless you have some very high-end charts, charting equipment. For most of us, with our normal GPS and our paper charts, we have to use tenths of a minute. The longitude scale, which is at the top and bottom, is never used for measuring distances. It's a very big point because a lot of people will use that and can't figure out why they cannot get correct answers. And the reason that's not used is because the 1 minute equals 1 nautical mile only at the equator. As it goes to the poles, these distances shrink and you get very inaccurate information. Again, latitude scale, 1 minute equals 1 nautical mile. We do all our distances off of that. When we look at latitude, longitude, how we read the scales here is very important. And the big point I'd like to make is that we read longitude from right to left. A lot of people will take like the 7130, and if they're reading from left to right, the next minute over they will say 3132, where in reality it's 2928. As you can see here, we got 7130 going over to 35. That's 5 minutes. You see the little tenths. So if we read from right to left, we'll go 71 degrees, 30, 31, 32, 33, 34, 35 minutes. And the same thing on the latitude scale, we read from the bottom up. Here we have 41 degrees, 20 minutes. The next one up is 21, 22, 23. If you read the other way, again, you have a tendency to add and not subtract and use some very bad numbers. Directions. Direction is a point from point A to point B. So we're going from here to there. So we do the degrees on that. We have to make sure we read the right part of the compass rose. So here we're going from B to A, it's 155. However, if we're going from A to B, it's 180 degrees difference for 335. When I plot, I like to put a little bit of an arrow on my dead reckoning line, just make sure I'm reading the right set of rows. I understand which direction I'm going into. Again, this is one of those basic mistakes people make. Nautical mile, 6,076 feet. Statute miles, 5,280. And they're just enough of difference. Do not use a conversion factor. Please measure them. You're going to get better data, and you're going to be making sure that you're doing it correctly. How do we use parallel rulers? One of the issues is that people do not work well with parallel rulers if they have not ever used them before. A parallel ruler, to get a correct reading, you must square the ruler up with one of the latitude or longitude lines. If you don't, it's not square with the chart, and the reading you're going to get is going to be very wrong. So here we squared it up on our line, and then I'm able to read off the longitude scale our the longitude reading. Here it happens to be 87 degrees, 49.7 minutes. You notice it's tenths of a minute, not seconds. We draw our line. Now I want to find out what 40 degrees, 7.4 minutes is, and I find that on our latitude scale. In this case, I use our dividers. I put it on one of the latitude lines, and I find our 40 was 7.4. Walk it over, make my mark, and there I have a long location based on the parallel ruler and the divider. But again, a key thing is to make sure that parallel ruler is always squared up on either a lat line or a longitude line. Let's talk about some various location finders. Basically, 3-point fixes, set and drift, etc. Here's a classic situation. We have a ship's heading of 271 per ship's compass. Why is that important? Our deviation comes off the ship's heading, not the bearings. It's another one of those major errors people make. So we've taken our 3-point fix, and we're going to have to convert it from per ship's compass to true. You cannot plot PSC, you can only plot true, so we have to convert it. We talked about that conversion. Per ship's compass takes into account deviation, which gives us magnetic. And remember now, deviation changes with ship's heading. It's a very big part of this. And secondly, the deviation comes off the ship's heading and not the bearings. That gets us to our magnetic compass. The difference between magnetic and true is variation, which changes geographically. Okay. Now, here's an example of, again, the conversion. The little table on the right here, TBMDC, true, variation, magnetic, deviation, compass. Things have to happen sequentially. You cannot bounce around that. If we're going from true to compass, we add west and subtract east. And if we're going from compass to true, just the opposite. So here we have a true of 265. We factor in our variation. We then put in our deviation, and we come up with a compass heading of 270. On the chart, it's 265, but the helm is going to drive 270. To check our math, we do total compass error. And to do total compass error, we simply take our two variables, which is variation and deviation. In this case, they're different, so we simply subtract one from the other, the larger one being west, so we come up with total compass error of 5 west. Now, if we apply 5 west to 270, what do we get? 265. If I apply 5 west to 265, what do I get? 270. So that's the way we can check our math. So here we have our 3-point fix. Our ship's heading is 271, which off our deviation table, we get 001 west. And if you notice, deviation is the same all the way across, and again, it's based on ship's heading. Variation is the same because it comes off the compass rules, and again, that's location dependent. And we do our math, and we come up with a true bearings to each of those objects, which we can then find. We go to the compass rules. Now, another really, really big point is that little X in the middle of the compass rules. We have to be aligned up in that little X, and then the direction on the outside of the rose. Remember, the outside of the rose is what we're using because that's true. The inner part of the rose is magnetic. We're not using magnetic. So here we line it up. We walk it over through the little base of the buoy, and we have our 3-point fix. The key things there again is that we're squaring everything up properly with the latitude and longitude lines. We're making sure that we're taking our deviation off the ship's heading and not the bearings. We're doing our math correctly. And we should come out with a fairly good 3-point fix here. This is where we're located. Another way of getting a fix is through a running fix. And again, I talk about that in our presentations. I'm going to do a very quick review here. We have our DR. Our DR is our hypothetical course line. Based on speed, time, and direction, does not take into account weather factors, currents, winds. And it's where we think we are. So at 1000 hours, we take a bearing off a buoy, and we mark it on our DR. We then continue to travel for another 20 minutes and take a second bearing off its same object. And we should be where we noted on our DR. However, these are two lines of position, and they really don't tell us much. What we have to do is advance our first line of position at 1000 hours. The distance we should have traveled if we were not under any impacts from weather current. And it's a straight calculation of distance equals speed times time divided by 60. We know what our boat speed was. We traveled for 20 minutes. We should be right where our line crosses there, where it says 1000-1020. However, it does not match up where our actual bearing took place. Therefore, our theoretical does not match where we actually are. And in this case, we got pushed off to the left and ahead. And that is our new fix. We plot a new course from there and proceed. The key thing in a running fix is to make sure you advance your first line of position to where it should have been if there was no outside factors. And then again, we base that on 60 East Street. Set and drift. Set and drift can be very challenging. It shouldn't be, though. It's basically, again, it's a very sequential problem that we're going to solve. In this case, we have our 3-point fix where we're at 1000 hours, and we're on a heading of 243 true at 5 knots. At 1045, we mark our DR location. Remember, that's our theoretical position. It's simply based on speed and time, which equals our distance. So at 1045 is our theoretical position. That's why we also have the half moon shape. We should be there. And again, we're doing our math to calculate where we should be. However, we find out that we're really not at our theoretical position, but we're in a different location. So we draw a line from our theoretical to our known position. That gives us set. Remember, set is direction. Simply walk it over to the rose. We can measure that off. Yes, we're at 211 true is our set. That's the direction the current or wind is pushing us. Next, we want to know how fast that current and wind is pushing us off course. It's not that distance. Distance does not equal speed. It's got to go through a formula. Here we have 1.8. We will push out 1.8 nautical miles times 60 divided by the time we were under that influence, 45 minutes, and we get a set. We get a drift of 1.2 knots. So our set is 211 true. The drift is 1.1 knots. Now, let me break this down into 6 very simple steps. 1 is our location. It's our 3-point fix, or 3-point fix we took. 2 is our theoretical position based on 60 East Street. Speed, time equals distance. 3 is our new location where we are at based on another fix. So we always go with the saying LLF, LLF. location, line, formula. If you haven't done a formula for step 3, can't possibly find out where you are. Let me go back to that. The second one is between 2 and 3. We've measured that. Here's our new locations. Where number 3 is. Here's our second line, and we have to do that formula a second time, this time to get speed. Okay, ETA, expected time of arrival. We need, again, certain factors. Either we need a distance, a speed, or time. We need 2 of the 3. In this case here, we're leaving point A at 9:37 in the morning. We're going to travel at 5 knots on a ship's heading of 104. We know how far we're going to go because we can see it on the chart and we can measure that distance, which is 12.7. So we take 12.7, which is the distance, times 60, divided by 5, which is our speed, and we come up with 2 hours and 35 minutes. So to go from one location to the other at 5 knots, it's going to go over 2.5 hours. We add that 2.5 to our start time, and our ETA will be 12:12. Again, it's based on our best estimate based on the conditions that we know. Let's do a speed make good. Speed make good is our average speed over the ground. Again, we have a start point, we have an end point, and we have a distance we can measure. And we travel that in 67 minutes. How do we know that? Well, we timed it. We have a start point and end point. The difference between them was 67 minutes, and we knew how far we traveled. So when we again work through our formula, it comes out at 11.4 knots. So we did our speed make good by measuring that distance, and we knew how long it took us. We plugged those 2 variables in the formula, and it gave us our speed. Relative bearing. If you use heads up on radar, you're using relative bearing. If you have a person out in the front of the boat watching for obstructions, they're also using relative bearing since they don't have a compass up there. So here we have a heading of 271 true, and we want to take a relative bearing of some buoys. By looking at the front of the boat is 000 or 360, 90 degrees off to our right is 90, right behind us 180, off to the left is 270. So here, the person out in the front of the boat looks back towards those buoys and says, hey, relative bearing about 135 degrees, relative to the front of the boat. All we do is add the relative bearing to the ship's heading. So, and if it's over 360, which doesn't exist, we simply subtract 360. So here we had a 271, which is our ship's heading, the true. The relative bearing of 135 equals 406, which does not exist. We subtracted 360, and we come up with a true bearing of 046. We can actually, we already are, we can find that buoy and draw a line, actually get us a line of position from where we are to those buoys. You're going to run into distance, we're going to run into relative bearings. It's really important. It's real simple. All it is taking your relative bearing plus the ship's heading equals the true bearing to that object. So we're 360, we simply minus 360. Okay, distance off. There are times we want to know how far we're going to pass an object. Not that we're going to go to that object, but how far off we're going to be when we do pass it. So first thing is we plot our DR, our course. Secondly, we identify a chartable object. So on a chart, then we have to use a different method. We do our closest point of approach is a 90-degree angle from our DR, or dead reckoning line. So here we do a 90-degree angle, our closest point of approach. Oops, and then we can measure that distance. So we know that we're going to be X nautical miles off that buoy when we pass it on our present course. So all there is here is 2 lines, our DR line and a 90-degree angle off our line to that object. It's that simple. If I want to do an ETA to our closest point of approach, I'll measure the distance from a start point to that CPA, and then do the math just like we've done earlier. What if it's a non-charted object? It's very simple. Say it's a military vessel and we got to be at least 1,000 meters off of it. There's our DR. We always plot our dead reckoning line. This is where we're planning on traveling. I then take a bearing at a particular time to that object and I plot it. It's a line of position to that ship. I travel a known distance. How do I know the distance? Because I did speed and time, ran it through 60 straight, and in 20 minutes I should be at this location. I now draw another another line of position to that. Where those two lines cross is where the ship should be. And then I simply do our closest point of approach, and I will know if I'm going to be more than 1,000 meters off that military vessel. Again, we're basically triangulating that location by taking two lines of position at a known distance apart, and where they cross, that's where the ship should be. A couple other items to remember in navigation are publications. Coastal Pilot tells us everything there is about an area that cannot be portrayed on a chart. These include harbor regulations, includes features, just a ton of information. It's published by NOAA, and it's updated, I believe, weekly by NOAA, and you can download updates on your cell phone, your iPad, whatever. But it provides us information that cannot be portrayed on a chart. The second publication is the light list. If there's an aid to navigation, has an aid to navigation number on it, it will be in the light list. And it will give us a host of information that we did in that publication, either different things up like horn frequencies for foghorns or light characteristics, whatever. Light list tells us everything there is about aids to navigation, and it's operated or maintained by the U.S. Coast Guard. The third one is the local notice to mariners. The local notice to mariners updates all charts, Coastal Pilot, light list, among many other things. So what updates all our publications and our information we need? Local notice to mariners, which is published weekly. Aids to navigation, a couple of light frequencies we want to keep in mind. Remember, a bifurcated preferred channel marker is always going to have a group flash of 2+1. It's the only type of buoy that has them. Quick flash, 50 to 70 times per minute, is caution ahead. It wants to get your attention and tell you there's a change up ahead. It does not necessarily mean danger. It could be the first buoy on a long chain of buoys, series of buoys. Morse code A, safe water, pass on either side. So MO A, which is a short, long light frequency, will only be found on safe water buoys where we cross on either side. Western rivers, buoys are not numbered, and we use this right and left bank descending terminology. Intercoastal, basically we have our squares and our triangles that are colored yellow. So intercoastal is marked by yellow. The U.S. marking system is all the other things we've talked about, being laterally significant. We got our red even triangles, and we got our green odd squares. And the key thing on this is you got to remember if we're going out to sea or returning from sea. It may be red right returning, but it's definitely green right leaving. And again, I would go through that aids to navigation that we have within the book that explains the various aids to navigation in that presentation. That's a quick review of coastal piloting. Again, if you haven't, make sure you go back through all the presentations and do the work exercises. And if you have, hopefully this will give you a good overall feel for coastal piloting. If you got any questions, please email me. I'll be happy to answer them.